We're very happy to welcome Professor Tobias Kaupp. He's the director of the Centre for Robotics, CERI, and that is part of the Technical University of Applied Sciences. Oh, I think Tobias, you're going to have to say the full name because my German isn't so good. But we're really excited to hear your talk on collaborative robotics in German manufacturing and logistics. And I know you've got a lot to cover today. So I'll hand it over to you and we'll have some time at the end for a few questions. And in the meantime, people can put their questions in the chat and we'll come to them at the end. So go ahead.
Great. Thank you for the introduction, Glenda. First of all, I'd like to thank the ACC for hosting me and Adrian and Usama, who are also in this call, my two students. So we've already spent a few weeks at UTS and we're having a great time. So today I'm gonna tell you a bit more about the work I do back home we've heard the title. So I'll see this works. Yeah, so just very briefly on my background. Australia is my second home, so I've already spent more than 15 years in this place, and I actually started off at QUT doing my diploma thesis. So you can see this picture here, that's on top of building 10 when I was testing out the antenna I built back then in 2001. After that, I moved to the ACFR and did my master thesis. So I found this nice picture on the web actually in Sydney Harbour of myself. Then I did my PhD for 4 years at Sydney Uni and started a company together with two colleagues from the ACFR back then called Marathon Robotics. So we make autonomous robotic targets for marksmanship training and tactical training for military and police. Some of you may have heard about them. We also did a bit of an excursion into delivery drones. So this picture is also from Brisbane, actually, where we worked with Australia Post back then to deliver packages on Brisbane suburbs. So I'm still involved with that company, but my main job is now being a professor at THWS, and I spent the last 5 years establishing the Centre for Robotics there. So the outline of today, I shortened it a bit, so it should be okay for 45 minutes, but I'll mostly talk about the applied research we do in two areas that are both relevant for the ACC, cobot-assisted assembly and manufacturing, and mobile manipulators for smart factories. So just briefly on our university, I know it's hard to pronounce. Wuerzburg and Schweinfurt are the two cities, so they're in the northern part of Bavaria. Can you see my mouse, by the way, when I wiggle that? Yep, okay. So 100,000 people and 50,000 people. So it's further from Munich than it is from Frankfurt, but it's still Bavaria, which is actually a good thing because they have a lot of funding and put a lot of funding into research and robotics recently. So we have 10 faculties and also non-technical faculties, but everything technical is in Schweinfurt, and that's where we are with our Center for Robotics, which I'll about next. So the Center for Robotics got funding mainly for teaching robotics, actually. But we are hijacking some of it for research. So our team consists of like 9 professors with different backgrounds. We are hiring the last one to actually in the next couple of days on Friday. But yeah, the team is almost complete. We got technical staff and admin staff, and we do applied research. So the applied research is funded separately by government research grants in conjunction with industry. So at the moment, we have about 7 PhD students and supported by master students like Usama and Adrian for research. The one differentiator of the University of Applied Sciences is that we don't usually have postdocs. So that's a bit of a challenge. So there's PhD and there's faculty, but the layer in between is missing. So we'll see if we can improve on that going forward. As I mentioned, the funding was mostly for teaching, so we established this Bachelor of Engineering in Robotics course separately. It is taught in German and in English, so we got both languages as one of the first ones in Germany overall. We had about 3 intakes, so the first graduates will release into industry very shortly. And there's a big labor shortage in Germany, especially in robotics, so we're trying to address that with our program. And yeah, we'll see how it goes when they end up in industry, but I think we're pretty confident. We also have some space. So we got 5 well-equipped labs in an interim building, and there's a new building. The Bavarian Premier just announced to spend 120 million on it. So yeah, this will take a few years to establish. Okay, over to the research now. So we do our research as part of the Institute Digital Engineering, which is set up to do interdisciplinary projects with regional industry. So apart from robotics, we also have a center for AI, additive metal printing, and intelligent production systems. So the idea is if industry approaches us with certain requirements in Industry 4.0 project, we can pool resources together and jointly interdisciplinarily work on those problems. For robotics itself, as I mentioned, those 2 areas I'm going to talk to you about today, those are the 2 I established so far. And we are working with industry. So Schweinfurt has a very big industry base, mostly related to automotive. So second-tier suppliers, you may know some of them. There's also quite a few SMEs around. So I enjoy working with them as well. It's often quite less complicated than with bigger firms, to be honest. But yeah, both types of end users are very useful to work with, and it's good fun. And we also work with technology partners. For instance, Universal Robots is in some of our consortiums as well. Okay. So first part, cobot-assisted assembly and manufacturing. So one big area I'm focusing on is human-robot collaboration. So the idea is to have humans and cobots and a worker guidance system work together with the idea of jointly assembling goods. So I'll show you a little video which will illustrate what we're trying to do. So we set up this demonstrator initially. And you can see here the human and the robot are working in parallel. That's always good. If they work in parallel, it's productive. You also notice a so-called worker guidance system. So we project things onto the workspace here, instructions for the humans, warnings, etc. And you can see here the projections again. And you see here this type of collaboration, which could probably be called cooperation because they have separate work areas. Next, we can see an example of a collaboration. So that means working closely at the same time on the same product with human and robot. So the robot just brought this axle, and the worker is now attaching this axle. So the robot is a third hand. So this is a simple example of a closer collaboration, and we indicate it using this yellow frame here in the middle. You will also see, like if you just missed it, this button was just pressed by the person. Yeah, so basically the workflow is in total control of the worker here. So yeah, so is the system smart? No, not really. Everything's pre-programmed. The person is in control of the workflow with this button. And thirdly, the human robot assembly sequence was completely handcrafted. So who does what at what time needs to be done from scratch for every new product. So we're trying to address those shortcomings in our research. So we applied for funding for a 3-year research program to address some of these. So the goals here are, so we got this approved, we're halfway through already. It's the Bavarian Research Foundation that funds it. And we got 2 PhD students working on it. So the goals here are automatically deriving these assembly sequences from existing process and product data. So rather than handcrafting, we want to generate the assembly sequences. And secondly, once we have those, we want to adjust them at runtime depending on the situation. If humans are involved, things may change. We want to be able to adapt and monitor the progress. So I got a little video for that as well, which we call the process chain. Let's play it. So the input data into the system is basically like step files, for example. Yeah, CAD data. This is a very simple assembly of a few Lego blocks. There could be other input, I'll show you later. So 2D drawings, for instance. And the first thing that happens now in our framework is the extraction of data into a so-called dashboard, and the dashboard is then presented to product expert. So the product expert can review what has been automatically extracted. In this case, we'll see those individual Duplo blocks are identified as components. And more importantly, this relationship matrix has been established. Yeah? So how do the individual components relate to each other in terms of the assembly? And other information can also be added, which may not have been available from the product data that was fed into the system. And what pops out of it is shown next. Here, for this very simple assembly, we got like a sequence plan where the human does this step in parallel to the robot, and then the third step is done by the human. And there's some projected times as well. And also there's a second option here where the robot does step 1 and human 2. Yeah, so there could be several options coming out of this system. Now over to the runtime execution stage. Once this assembly sequence plan has been generated, we can actually automatically generate robot motions. We use generic functions for that. So here you can see one, we call it reach and grasp and carry, and the last one is release. So those are generic functions that need to be parameterized at runtime, but apart from that, it's generated. Yeah? No one wrote any code. And we can do actually the same thing on the human side. So we can generate instructions for the person, for the worker, either shown on a screen like shown here, or also projected onto the workspace. This is shown here. Okay, so based on that, for that to work, we also need certain technological components. One is object detection. So we need to detect where are the objects on the workspace. Another one is safety. So we separate those areas visually. And we also track when the human hand is close to the robot. So we slow down the robot automatically. This body tracking we also use for something else, which is called anomaly detection. I'll talk a bit more about that later. All right, so this is the whole chain. And I want to show you one of our products here. This one on the bottom right. That's a more complex product we want to eventually be able to assemble using the system. We have a handcrafted solution again for it, but we want to automatically create it now. All right, so a bit more details on those components. So the planning framework is, we call it extract, enrich, plan, review. So published in the paper shown below. So the extraction I just talked about is automatically from, for instance, CAD files, and enrichment is what I showed with the planning dashboard. Yeah, so things like relationship matrix between components, joining methods, like is it going to be bolted, is it going to be glued? This kind of information goes into here, again, either by the product expert or by the data that's already available. For task allocation, we rely on profiles, or we call it skill matrix. So user profiles, for instance, one person could be right-handed, the other one left-handed. Yeah, you do things differently with those people. Or you have also skills for robots. Yeah, certain kinematics can do certain things, others cannot. So if you put those profiles in the back end, then we can make use of that information for the planning. At the end of the day, we also have some weights for cost, quality, and time. So that means what is, for this product, what are the relative importances of those 3 factors? Again, that could be a product expert that inserts it. And the cost is very important here, quality less so. Mostly all 3 are important, but yeah, there's some relative weights. Okay, so once we got that, we can make those plans. So first step in the planning unit is to generate a generic assembly sequence. And that's shown here again. Yeah, so this is our example of that toy truck. You can see there's some parallel activities here. That's was shown in the video as well. So the bottom part can be assembled independently of the top, and then it goes all together. At this stage, there's no allocation yet to humans and robots, and that's why we show it all in gray color. But this changes in the second step. That's shown on the next page. So we fill the assembly sequence with color. So the green one is robot and the blue one is human. And you can see 4 different sequences popped out of our system here. The first column here is related to human-robot cooperation, and the second one, collaboration. So some of those details I don't have time to talk about. You can see in the paper, but just to emphasize, there are 4 different assembly sequences that popped out. And then we try to evaluate those based on process time or cycle times, which is based on MTM, the methods time measurement. So these are not actual times, but projected times. And the baseline we created was pure human assembly. That's another option that may come out of the system, and which took 89 seconds. And then for cooperation, you can see human and robot are working sort of in parallel with some synchronization points, and we got 77 seconds. And for collaboration, we actually got a longer time. It took longer, but collaboration may have other advantages like ergonomics, for instance, not in this case for the toy truck, but in general. So I think you get the idea of what kind of thing we're after, and we are just trying to get more complex products under this framework and test it out. We did an extension though, so that's the next page, that's another paper. So we extended it to also include 2D drawings. So you can see here on the right, here are the step files, but 2D drawings can also be fed in. And those are often very useful for product variants. You can see an example here. This is a component from one of our industry partners that has this measurement A. It's hard to see, but this measurement here, depending on which country you deliver the product to, this varies. So there's product variation represented in a table. This information you can actually extract out of DXF files automatically. So now that information is available. And the third one we thought would be very useful is assembly instructions. So for all those manual assemblies, you usually got instructions how to assemble it. So we tried out some natural language processing models to extract components, like this one here is an example. Connect the pipe to the valve using a wrench. So we can extract action verbs like connect, components that are used in the assembly, and tools. So we used a pre-trained model, and it didn't quite work. We got verbs and components, but not tools, based on German newspaper data. So apparently not enough tools in the newspaper. So we created our own data set with ChatGPT and used some transfer learning, and then we managed to extract all 3 of those based on instructions we got from our industry partners. So what we end up with in the end here is, we call this a data model. So it's a hierarchy of the assembly. So we have the full product on this level, and then sub-assemblies and components. And you can see we are now able to add tools and actions. And we are also able to add the variations here of the components that may exist. And once you got the data model, you can use it again for generating assembly sequences. Okay, so this was planning, and now on the execution stage, we started looking at human action recognition during assembly. So here's an example of a simple assembly where we add an adapter plate to a gearbox, again from another industry partner, and we have to tighten 4 bolts. And most of you who have changed the wheels of your car know we have to go diagonally, not around in a circle. Same here. So the intention is to, there's a certain intended path, which is you start with B1, then B3, then B2, then B4. And that's shown on the left here. These are the steps. And so we trained an autoencoder model to basically detect whether this path is followed or not. I'll play the video. So under normal conditions, you can see the body pose tracking. If the right motions are done by the person, then nothing happens. It's all good. And another possibility is that the person does something slightly different but still correct. For instance, you start with this bolt here and then go to 4 and then 3 and 1. That's okay. So we can detect it, and we call this a green anomaly. So it's an anomaly, but it's allowed. So what happens here is we show on the screen, it will come up in a second, on the workspace, an alternate assembly path detected, but it's acceptable, right? The more interesting one is when you do it wrong. So I'll show that, which we call a red anomaly. So now the motion of the hands is going around in a circle, and our detector, shown here, the anomaly detector will see that, will check that, and then post something on the workspace here, wrong assembly. You have to do this again, go back. Yeah. So this is our first kind of approach in this field of action recognition. I know like Luis Fernandez is also working on that with Michael, and so we've already started talking. I put them in touch with the with my PhD student back home, so already some collaboration happening between other programs as well. Okay, so I want to emphasize as well the work of the master students in this project. Usama was working here on the object detection. So as I showed at the beginning, we need to detect the objects on the workspace, and Usama implemented a template-based algorithm called LineMod, and completely implemented it from scratch again. And so he's basically it's not a learning algorithm, but a template-based algorithm. He's generating those templates based on color and depth information offline. And then in real time, the template matching is happening with the real images. And then there's some refinement process using ICP. And then we can get the 6D pose on the surface here for those components. And Adrian is working on the task-centric robot programming, those generic functions I mentioned briefly. So you can see here this component we call transformer. So the assembly steps from the planning unit get fed in, and we have known objects from the database, and then from Usama's component we get the 6D pose estimation, and using that information we can now parameterize the generic functions. So we can see the parameters that are required that come from these three inputs for each, and we have one for each one: grasp, carry, we've seen those already, release, and we extended this framework with also a joining operation. So here's a very simple one, we call it press. So in general we need others like bolting and gluing and so on, but you can see this is easily extendable, this kind of system with generic functions. All right, so this was task-centric robot programming. I also wanted to show one slide on the work we've just started on user-centric robot programming. So there's some overlap with your program too as well. So we are working with a company that builds welding robots, or they actually do welding design, but they build this robot, very nice, has a UR10 on top. We gave them advice to use that. And they are now asking us to basically help us with programming automatically. So we have a team of undergrads currently working on that. They're pretty good. So there's interesting results. We want to use camera technology, line scanners, and prior knowledge like CAD data, teaching all of those combined, and to be able to teach welding paths like shown here. Related to that is also other projects like this is from the automotive industry. It's called this is a car seat. It's the foam of the car seat, and it needs to be cut. The seam needs to be cut. These are deformable objects that have high tolerances, so you need some sensing approach to figure out which path to take here. So yeah, I got a PhD student starting actually next week, also on these kind of problems. One idea is also to use augmented reality for programming paths and programming robots in a user-friendly manner. Okay, so far I've talked about assembly. We also work on disassembly. So robots can be very useful for that as well. People talk about the circular economy and sustainability. So products have a life cycle, and you need to think about what to do once their life cycle is over. So the TU Munich started a competition called Robothon Grand Challenge, which is about recycling of e-waste. It has taken place 3 times so far, this competition, and we won it twice. So we like this one. So what it's all about is you get this task board sent out, this black box you can see here, and you have 1 month to solve certain manipulation tasks. And then the second component is to also bring it into the real world. For instance, here we remove batteries from a calculator. So I show you a little video from 2 years ago. So the first thing is you place down the taskboard, and the system needs to detect it and localize it. That's the first task. So in the previous year, we opted for an approach where we have a rough image, a rough localization using image processing, and then we touch the sides for fine localization. So this is not uncommon in industry to do that approach for localizing objects. And from then on, you can start manipulating, and I'll just show you some of the tasks. So here, a key needs to be inserted in here and turned. And by the way, I forgot to mention this taskboard is completely instrumented. So it has sensors inside, and it has a microcontroller that's shown here. And so it can record the times it takes, and it can also register successful and unsuccessful tasks and so on. So here's an exciting bit, removing batteries. And they need to then be inserted into those little holes here. So pack-in-hole sort of application. And we came up with a pretty pragmatic solution to put those things upright. So you can see that. And that's not very accurate, as you can imagine. So we now used a spiral search with force feedback to insert it. We came up with better solutions after, but it's cool to see how it develops and how sometimes pragmatic solutions get you to the goal. Okay, so this year, in 23, the focus changed a little bit, and it was all about taking electrical measurements. So I'll show you again a little video. So now our vision system has improved a lot, so we can just take a quick photo and we know exactly where the taskboard is. There was another vision task here where we need to detect those triangles and move that slider. And then after that, the measurement was supposed to be taken place. So we opened this hatch using the probe to save some time, and then take the measurement. And the exciting bit is coming up, which is winding up that cable. So again, deformable objects, not solved in general. So we made this little hook, and now are winding up the cable. And important to note is, again, this has to work in all orientations of the taskboard there. So you can't completely pre-program this. You need to do some things that it works for under all conditions. So the other part I want to show here is now the transfer into the real world. So we came up with an idea of diagnosing PCs. So here you can see a standard, like a connector we printed, goes to a standard interface of most computers have. And then we connect up the other end to a oscilloscope using this little board. And now we can read out error signals from the PC. So I don't know if we can hear this annoying beep. Most of you may know when the RAM is missing. So now we know that the RAM is either faulty or missing, and we use a YOLO detection to see, is it actually there? And if it's there, we swap it out. As you can see the robot going in there, manipulating the RAM bar, and also the same thing we did for the GPU. Yeah, so this is kind of could be a useful system for recycling and testing of components. So we made this little table here where you can see that some of these terms the sustainability people talk about, these upcycle types of repair, recycle, and reuse, could be realized with a system like this. So potentially this could be useful for recycling down the line. Right. So we also try to get some quantitative data. I don't have time to talk about the details, but it's going to be hopefully in a paper if it's accepted soon. So we did some experiments here at UTS on human performance, just very simple pilot experiments. How quickly can a human wind up this cable or do these little things? Yeah. And it turns out humans are still better than our best automated solution. But also there's a higher variance. Yeah? So as expected, people are different and do it differently. So the variance is higher, but the mean or the median here was actually better than the automated solutions. So we're thinking in this area of disassembly, human-robot collaboration could be a good approach again. once it gets more complicated, once you have mechatronic systems that need to be disassembled in an unknown state, I think I can imagine that the combination of human and robot skills would do pretty well. So that's an area we wanna do some more research in. Okay, this was the first part. Second part is now mobile manipulators in smart factories, or you can call it cobots on wheels. So we are working also on a three-year research project here, almost 3 quarters through, development of a mobile picking robot for warehouse commissioning. So you can see here in this picture, there's a warehouse with pallets that have uniform packets on it. And the robot goes around and picks these packets and establishes a so-called mixed pallet. And the mixed pallet is what will go out to the supermarkets. So this is done with manual drivers at the moment, and the goal is to automate it. And even in the challenge is mixed operation, so humans and robots will work in the same space doing the same task. So we do this with Linde material handling. Linde makes forklifts and has big customers that have lots of products in big warehouses. So Linde focuses more on the integration and on the hardware in this case, and we can focus on the perception for manipulation of objects. So the challenges here for this object detection task is the big variation of the products. So we got about more than 1,000 different products. It has to be possible to add new products easily. They come out all the time. And the particular thing here is that we have lots of instances of the identical object class. So often in object detection, you have different classes, cats and dogs and whatever else. But here we have just one type, but many instances of it. So that makes it kind of a special problem. We took 2 approaches so far. One is machine learning based, using semi-synthetic data, and the other one is geometric. And I'll show you some of both of those approaches. Okay, let's start with the machine learning. So we know we need to do package detection and instance segmentation, basically. So the requirements for any sort of data set for machine learning is it has to be large. That's always true, mostly. We want automatic labeling. We want high variation. It needs to be realistic and extendable to new products. So what we opted for here is using a synthetic environment, but adding some real information. And the real information here is the texture. So you can see here, this is a real photo of some of the texture, and we add that to the synthetic data set. What we can also do is vary it. So this knife symbol that can be seen here is removed, and then we can also vary the texture slightly. And then, of course, the rest is standard domain randomization. We can use different backgrounds, different lighting conditions, different camera angles, and so on. So yeah, this is our basic approach, and then we try to train some networks. So the guys are still working on different options here. We've tried just the YOLO version 4 with the top view here. So if you look at that, here some qualitative results of robustness. There's a bit of a lag between right and left, but you can see if you remove some of those packets, it still is robust. It detects the next layer here actually already, and so on. So we got reasonable results here. And then we moved on to instance segmentation frameworks like YOLACT and MaskRCNN. And we trained it with 10,000 semi-synthetic images and then tested on real images. And the results were okay, pretty good. So you can see some of them here. There's a little video at the bottom which shows you the MaskRCNN results, again, trained on one particular package. So this is one specific package, and we got fairly good sim to real results. But what we really want to build is a generic detector, that doesn't just work for one package, but all types. So we're working on that at the moment and improved actually our automatic labeling scheme and use YOLO version 8. And this combination looks quite promising. So this is cutting edge results. I just inserted this last night in my talk. So yeah, they're making good progress while I'm over here. So that's good to see. also, like we want to build an end-to-end system, so we're working with that industry partner, as I mentioned, and yeah, to actually grasp packages. Yeah, so we build a complete pipeline in ROS from images to grasping poses. So here's another video I got last night of, you can see the grasping poses in the middle of those packages. And here we're just showing that the detection is robust when you remove packages. He didn't add any, he forgot to add again, but that should work as well. And finally, some actual grasping. It's down a bit. So yeah, this is a prototype the industry partner built, and we can now basically, it's not that exciting, but always good to see when something is actually working. So that's some result of grasping it using that pipeline we built. So you can imagine there's a fair bit of software architecture as well to build. All right, so this was machine learning. Another approach I mentioned before, geometric approaches. So we realized we have a highly symmetric problem here, a highly structured problem. If you look at this picture on the top, so if you manage to extract like 4 corner points of one package, and you get the length to width ratio, and using that ratio, you can basically predict where all the other corner points are of those packages, or likely are. So they are candidates. So for instance, here you can see this one and that one are not actual corner points, but there could be some depending on the package pattern. So we can predict where they are likely are, and with some error model as well. So the further away you are from the center package, the bigger the error in this direction. So if you combine this corner detection with some edge detection at the bottom, then you may be able to reconstruct this pattern completely for this very structured layer. And then, yeah, you're done. You can compute the gripping poses. So it's another direction we're taking, and potentially there's options for hybrid approaches and combining the two. Okay, so this was the industry project. And now over to RoboCup. So we're also participating in the RoboCup at Work competition. So there's a lot of overlap with this other project. So the same principles work on both. So one's in a competition setting, the other one in an industrial setting. So we participated a few times now, and just in the international one for the first time. I was there for the whole week. It was very cool to see everything coming together. So here are some impressions of our robot moving through this arena, autonomously navigating and picking up objects and delivering them somewhere else. So this is it can be summarized like that. Here you can see it's looking at some objects, detecting them. They're hidden behind this box, but you get the idea. Picking it up and transporting it somewhere else. And there's always an applause if something works. Right, so to give you a bit of an idea, this competition, the way it's set up, they call them tests. So as part of this 1 week of 3 or 4 days RoboCup, we had like 6 different tests, and increased the number of objects going and the challenges for perception. So for instance, the backgrounds are changed from white to something else, like this brown one or the green one. The objects sometimes need to be inserted into those boxes, red and blue. There are more challenging shelves, like a rotating one here, which is basically simulating a conveyor belt, or inserting objects into cavities, like any toddler can do, but the robot, not many robots can so far. So yeah, so this gives you an idea in terms of navigation. You add some obstacles that were not in the map, or you add some of those marker tapes on the floor. So you need to detect the floor tape and as a virtual obstacle and things like that.
Tobias,
yeah.
sorry to interrupt. We have about 5 minutes left. I was just wondering if there might be some time for people to ask some questions.
Yeah, okay. Right, okay, I'm almost done. So actually, yeah, we don't have to go through all the details here. So the perception system we built is very similar to what I showed before for the other framework. And we also put a paper in, so hopefully the details will be published very soon. there's other industry applications we do with mobile manipulators. And another interesting one is moving things between production cells. So here is a machining center that needs materials and tools, and that can also, mobile manipulators can serve that need of transporting things to and from them. So yeah, just very quickly, I also want to just give a brief outlook on what we are doing here at ACC with Adrian and with Selma. So we're working on program 1, and we are building on top of work from like Alain and others on flock GPIS for creating those distance fields you can see on the bottom right. So I'm reconstructing the ACC logo here. And as a side benefit, you get this distance field, so you know for every point in this space how far the obstacles are away or the structure. And we want to use that for human-robot collaboration manipulation tasks going forward. So we started working on the software framework and making good progress. So hopefully we'll be able to report a bit more going forward. So yeah. Sorry, I took too long, but yeah, we'll leave some time for questions.
It's just so much. It's so brilliant. Love it all. I do imagine that there'll be some questions we have time for maybe 2 questions from the audience, and this will be recorded as well. So sure. It has been recorded, right? So I think, yeah, bravo. It's excellent. So exciting to see. Now, anyone want to ask a question? I mean, I can see all the overlaps for everyone. Is there a question there, Maren, in the room?
Yeah. All right. Well, I'll ask one. Thank you, Tobias. That was very exciting. Marcus from Program 2. Look, I'm really interested in the aspects of human-robot interaction. And in your first assembly task, you had this system detecting the human making a correct or incorrect assembly. I was really interested in that. In our experience working with our industry partners, it's often not black and white, what is correct and what is not correct. So we're thinking about soldering or welding. It's very complex to determine, what's actually a correct approach. And I think it's really important to also acknowledge inter-individual differences in how people work and how people perform tasks. So I'm just wondering whether what your thoughts on that were in terms of how that could be accommodated in a system like yours.
Yeah, exactly. That's something we want to address as well, the individual differences. So one simple way to address it, I mentioned the example of putting profiles into the system of right-handed, left-handed, things like that. Of course, there are privacy issues and things like that we have to also check and address. But even at the planning stage, you can already accommodate the particular needs of individuals, I think. So you can imagine someone logging in with his ID, and then the profile is right there, and then the assembly sequence is generated differently. So that's planning, but even execution, that's your other point, adjusting to the needs of the person, that's something we want to achieve eventually. This is tricky, but I want the workflow to be guided by the human, not by the robot. So far, people adjust to the robots, and it should be the other way around, really. So if a person is slow on one day, just slow down automatically a bit, and the other way around, like humans do it when they work together. This is a long-term goal that's not easy to achieve, but yeah, we definitely we're thinking about that too.
Yeah, great. Thank you.
All right, we are at 11, and I think people know how to reach you, how to find you. So if they have more questions, I know I certainly want to talk to you about the teaching side of things. So maybe when we come down to Sydney, we can have a bit more of a chat about that. Yeah, but until then, thank you so much for sharing all of that. Really fantastic and so exciting. So many overlaps with the stuff that's happening in our center. So it's fantastic. Thank you for sharing, and congratulations to all your team.
Thank you. Yeah, it's very exciting to see. When the ACC came out, I couldn't believe it. Yeah, this program is so similar to what we are trying to achieve. So yeah, I can totally imagine that we can learn from each other and keep this collaboration going. And this is just the first step. Yeah, the students are welcome to come and see and spend some time with us and researchers as well. So I can see a a longer term collaboration being very useful for both sides.
Brilliant. Oh, that's so exciting. Well, have a great day, everyone, and we'll see you next week. Everyone take care and see you soon.
Bye.
Bye.
Thank you.
Thanks. Bye.